Hello and welcome to TidyX episode 175, TidyX screencast where we go through and explain how our code works. My name's Ellis Hughes.
And my name's Patrick Ward. Thanks for checking in at TidyX. Episode 175, we've been doing our 20 minutes, what can we learn in 20 minutes segment. We've been working through predicting pitchers into the Hall of Fame. We've used basic frequentist logistic regression. We've used Bayesian logistic regression and pulled out the posteriors and showed what distributions look like. Last week, we used some deep learning
AI.
where, we used some AI, neural network. And this week, we're going to use random forest. We're going to, more explicitly, we're going to use random forest within Tidyverse. And we're going to show how you can use the power of the Purrr package, which is a Tidyverse, loaded in Tidyverse, the power of the Purrr package to use map functions and lists in order to tune your models. And then we'll use things like metrics to evaluate the models, and Broom is there if we want to pull out a tidy version of the model. So
Yep.
everything from 172 is still the same cleaning script. So if you want to see how we arrived at this data, episode 172, you're going to figure out how we arrived at this data.
There's a link at the top of the screen here.
Yep. Other than that, we're just going to jump right in with getting going on our random forest. So Ellis is going to load all the data in. It's already loaded.
Done.
It comes from the Laman baseball package. Thank you for that. It is free in R. It's an awesome package that we use a ton. And so here we go.
All right, let's do this. So the first thing we're going to do is we're going to make our lives a little bit easier. We haven't done this a lot. So far, we've been gluttons for punishment, but what we're going to do is we're going to rename the training data set. So pitchers eligible career stats Hall of Fame Sands 2018 final. What that means is pitchers, there we have their Hall of Fame and all their other career stats all summarized for their entire career. Everybody that is not from 2018, so it's all people that have historically been eligible and have gotten into the Hall of Fame. And final meaning we know their final results. Either they're definitely in the Hall of Fame or they're definitely not in the Hall of Fame. So if they're still eligible, they are not included in this data set. It's only people that have been accepted in at this point or are no longer eligible. So now we've got our training data set, but what we're going to need to do is random forest needs our values to be zeros or ones. They need it to be numeric. So what we're going to do is, factor. So we're going to convert the inducted column, which is a bunch of true or falses. It helps if I call line 119 to convert it into assign the train data set. It's all true and falses. If you call as numeric on a Boolean vector, falses become zeros, trues become ones. So we're going to first convert it into a numeric, and then we're going to say, hey, actually, let's turn this into a factor. So we're going to call as factor on that and assign that back into inducted class. And of course, we could have done that in one line. But now it's going to see it as two levels, 0 and 1. And it's going to know how to handle that going forward. So we can also then call a table on there. You can see that there are 553 people that were not inducted into the Hall of Fame and only 15 pitchers that have been into the Hall of Fame. So again, seems like if you want to be in the Hall of Fame, don't be a pitcher. Sorry. It's what it looks like. I don't know. I'm not making any judgments here. But let's get going and create our model. And the first thing we need to do before we do that is actually create our cross-validation folds. So we need to be able to select from our data set, because it's a relatively small data set, right? It's only 568-ish rows. It's not a large data set. So we're going to use cross-validation to help look at several different models and help evaluate the quality of our models. So we're going to set a seed, and we're going to use the function vfoldcv, where we pass in our training data set, but we're going to then specifically pass in strata. And because, as we mentioned before, the amount of people in the Hall of Fame is a rare event, there's not many of them, we need to tell it, hey, make sure that in every cross-fold, you have at least one person that did make it into the Hall of Fame. That way they can, when you're training the model, it is able to have both sets of both falses and trues in your data set there. And we're going to set V to 5, so we're going to use 5 folds. So we create that, and now we've got this new data set here called DCV, fivefold cross-validation using stratification. And we've got the splits column and the ID column here. And so now this is a list column containing a bunch of different splits. Patrick, what are we going to do next?
So now that we've got our data split out into cross-validation folds, within each of those 5 folds, we want to make a training data set and a validation set. And this is because we're going to tune the model. And all of these machine learning models have little knobs and levers that you can turn and twist and pull in order to get them to map to the data more appropriately. And obviously, there's going to be a trade-off here where the bias variance trade-off, where if you map them too closely to the data, they are horrible on any out-of-sample data. They just read the data back to you. So we want to be able to tune these levers, though, in order to find an optimized model and then make decisions going forward about which model to use. So to do that, we're going to split this each cross-validation fold into a training and validation set. So oftentimes people will split their data into training and test set, but that training set, they'll further split into a validation set. So for each fold, we have even a further train and test set that we're trying to see how the model behaves. And so we're going to use the map function here from the Purrr package, which is basically going to take a function, which is splits, which is going to split the...
That's a list.
Oh, sorry. It's not taking a function. It's taking the list of splits. Yes, the list of splits, and it's splitting it on this function training. Training is taking the data within each of those splits, and it's saying, okay, cut some of that data to the training set, and then the validation, cut some of that data to the validation set.
There you go. Wanted to make sure we're passing the most accurate information that we can.
Yeah, right. We got it. Okay. So we've got our cross-validation folds. We're ready to set up our tuning parameters. 2 of the more common tuning parameters that the random forest takes are the mtry, which is the number of variables to use within each tree of the forest as it goes through and makes these random splits of data, and then the number of trees, how many trees it's going to fit every time it makes a new split. The way I set this up was using the cross-validated data, and then I used crossing. And what crossing is going to do is it's like in base R where you have expand grid. It's basically going to take or create each permutation for us and do like a cross product. So we're going to have, for every mtry2, we're going to have entries 100, 200, 300, 400, and then it's going to go to mtry3, 100, 200, 300, 400. It's going to give us every cross product. So that's what crossing does. In my original script of this, before we get to that, the next thing that we do is I created this little string. And in my original script, I created this string because I was going to split the string between the mtry and the entries parameters when I fit this into our tuning model. And what we decided was going forward, which you'll see in a second, instead of doing that, instead of the way that I had a string split to parse out the numbers for each of the tuning parameters using a map2 function, Ellis is going to introduce us to the pmap function, which allows us to do parallel mapping. So different ways of doing this, they accomplish the same task. His way is a little bit cleaner than the original way that I had it written. But if you want to learn more about how these map functions work, because they're super powerful, like and subscribe on the YouTube channel and drop a comment down below.
Let us know. We'd love to go more into Purrr and all the different ways that you can deal with lists and iterating and whatnot. We've definitely done some episodes in the past, but I don't think we've done one where it's like, here's all the different ways you can use Purrr and do map2, map LGL, map int, all those different tools. Let us know, like and subscribe, like this video so that the algorithm pops this one up too to other people so that they can see how to use random forest as well. So interaction with this video in any way is really appreciated. So now we've got our CV tune data set here, printed that out. So now we've got our splits, our tests, our train, our validate, our mtry, our entries, and then the nice little string here to make it so that we can kind of keep track with our human brains what exactly we're doing here. We're gonna throw this and we're gonna do a bunch of tuning on our random forest here. So we're going to use CVTune. We're going to throw it into a mutate, and we're going to create a fit column. So this is going to be a fit random forest now, but we're going to manually fit it across all the different variables that we have. So which training data set, what are the mtry, what are the trees? And so the way we're going to do that is using the pmap function, or the parallel map function. What parallel map expects is a list entry here, where the list is every single value, or every single, it's a list of vectors, and every entry in that list is expected to be able to be evenly spread out across all of them. So basically, you should have the same number of entries in train and mtry or trees, or you can pass in one. So instead of trying to do all the different mtry, I could just pass 300, and that would be okay. It would just then use that first one. But what we're doing here is from CVTune, we're going to use this train column here. We're going to use params as mtry. In fact, I could just replace this with mtry. That might make it easier for folks to keep track of. And then trees. So this is the number of n trees that we're using here. And we're going to create this new temporary function, or anonymous function, and we're going to pass train into x. We're going to pass mtry into mtry here, and trees into trees here. And we're going to fit our random forest. So we have our model here. So for inducted class, we're saying this is probably predicted by ER, BB, SO, and SV. The data set we're going to be passing is X. So that's, again, that training data set for that row of the table there. Mtry is the mtry for that row, and n trees is the number of trees for that row. So we pass that in here, and it's going to now, for every single row that was in CVTune, train the model and go from there. And so as you can see, it trained relatively quickly. And now we've got this last column, this new column here called fit. And it's got a bunch of random forest fit models that exist in our data frame here. So this is like also the nice thing. We've kind of touched on this in the past about list calls and tibbles and how awesome they are. But here we've been building up this tibble over time, and we have our original splits, the ID, the training. You can go back and understand how that model is fit all the way back. So I think that's kind of fun and cool. But now we need to see how it performs. Patrick, how are we going to do that?
Yeah, so the first thing that we're going to do is, now that the model is fit, is make some predictions on the validation set. So we're going to basically do this by taking the RF variable or object that we just created. We're going to add in a predicted Hall of Fame column, and we're going to use map2, again, coming from Purrr. Okay, so we're fitting to this. We have our model fit, right? We have our validate, which is going to be, you can see in the bottom there, the validate list, which is inside of that list is a small data frame of each of the validation sets that we have. And then the function that we're going to use, which is specified with the little tilde first, is going to be predict, and we're predicting x dot x on dot x and dot y. So we're predicting the fit model onto the validate data frame of each of those lists. And that gives us now a predicted Hall of Fame column, which in this case, because random forest is a classification and we didn't specify probs, type equals probs, we're getting a class, 1 or a 0. So now that we have that, we can basically unnest the train column. Actually, should we be unnesting the validate column? Validate model. There we go. And we can unnest the validate model. We can select the 2 columns of interest. This will give us a smaller, this is a really wide data frame right now. But now we do the counts and we see that, well, okay, cool. We have some outcomes, predicted outcomes, and the actual class. And so what we're going to want to do from this, remember the validation is like our mini test set on each of those folds, because we were trying to tune these parameters, mtry and entries. So what we're going to do is we're going to use area under the curve in order to identify which of these models or which of these tuning parameters gives us the optimal model. So we're going to take that RF validate object, And we're going to use another map function. This is going to be map to underscore double. We're adding into this the X variable, which is the validate data set lists, the predicted Hall of Fame, which we just predicted. And again, the function now is going to be tilde AUC, area under the curve. And we want to look at the actual value, which is whether the person was inducted. It's going to be a numeric, yes or no. And I think if we're converting a factor to numeric, do we need to do -1 there?
Yes.
Yeah.
On not on that one. On the
No, on
validate.
that one, I think. Yeah.
Yeah.
And I think also on the predicted one as well.
Is that?
It's also a factor.
Okay.
Um,
But AUC is just the same. So.
but it's not. It's going to be the same because they're the same value. So yeah, you
Whatever.
don't have to do it. You don't have to do the -1. It'll give you the same. Oh,
Apparently not. Let's
redo it.
There we go.
Okay.
We were trying to be too big brain and change stuff on
So,
the fly here.
We have our area under the curve. So now we want to find out which parameters give us the highest area under the curve value. Area under the curve is a measure of discrimination in this classification model. So how well does this model discriminate between the two classes of interest? So we're going to group by our number of trees and our mtry variables. We're going to get the average area under the curve across each of those 5 folds for each of these types of mtry and ntrees permutations. And then we're going to slice the max. So, hey, give us the best area under the curve. This is going to produce the best model, which has 3 mtry and ntrees of 300 and an area under the curve of basically 0.74. So if we run that, we now have a nice little data frame called best model. And we can use that to select out the mtry and the ntrees that we're going to need to now fit our final model to the entire training data set. Now we have our final model. We have the optimized and tuned parameters. And when we fit that, we have a final model that is ready to go and make some predictions. First step we're going to do is make predictions on the training set. So we're going to predict the Hall of Fame class as predict train, new data equals train. And the other thing we're interested in is getting the predicted probability. So if we use type equals prob within that predict function, we get a data frame of both of the classes and the probability of those two classes. So there it is right there. So we're going to just bind that to the training data set, and I'm going to rename them instead of being class 0 and 1. I'm going to rename them not inducted or inducted. So now we have, there we go.
Just slightly changing this to make it easier to to see. So we're saying train, C bind this with those predictions, and then we're gonna have 2 columns. One's called 0 and one's called 1. We're gonna rename that not inducted for when it's 0 and inducted for when it's 1.
Yeah.
And now I've got our training data set here.
Awesome. And now we take a head there, and so now we have a nice little data frame that gives us the information we need. Next thing we can do is calculate our Breyer score, which is for a classification task is the mean squared error. So the class here is either a 1 or a 0, and we're minusing from that whether the predicted probability of being inducted, which that should be, okay, go ahead and.
I think we're good there. Yeah.
Okay. I think you need the 1, but yeah, you need the -1 because it converts it to a 1 or a 2. So now our Breyer score closer to 0 means nearly perfect predictions, which is basically what we have, where we're minusing the class 1 or 0 from the predicted probability and squaring that value, the mean squared error. And so it's nearly 0. So that means that our predictions should be almost perfect, which they are. And this is the training data set. So that's a little bit weird and wonky, obviously. Now, one thing to consider here, if we run this section, is we're taking the training data set, we'll grab a few columns. We're going to say, who are the highest probabilities to get in who haven't gotten in. So basically their inducted class is a 0, right?
Oh, or who? Yeah, who are the people that didn't get in, who didn't actually get in, that are the top predictions from our model?
Correct. The top predictions. Correct. So they have so it's the same guys that we've talked about: Kurt Schilling, Roger Clemens, those kind of guys. One of the things to be aware of is in these classification tasks, when you're predicting the class of interest, the default is to set the threshold at 50%. So these guys have not been predicted a 1 because they are not over 50%. You could, of course, change this if you use an if else. You could change it to say, I want my predicted class every time the probability is over 30%. And you might need to do that. The 50% default might not be good for your data depending on the prevalence of the outcome of interest. In this case, the prevalence of a pitcher going into the Hall of Fame was very small. It was 15 out of 538 potential players. So 50% is going to be a very, very rare occurrence, in which case you might want to lower that threshold so that you can capture more guys. Alternatively, you can move away from just making the direct, specific class 1 or 0 prediction and use the probabilities in order to calibrate how much certainty you have in whether or not the person will make the Hall of Fame or not.
So lots of different ways you can use this rather than just the black and white, like down the middle, 0, 1, 50%. That's it. We're not
Yeah,
thinking about this more.
yeah,
But cool. So now we've kind of seen how it performed on our training data set, but we already knew the answers there, right? Like it's the training set. How does it
yeah,
perform against the people that we don't know or are still waiting to find out if they get in, whether our model thinks they should get in?
yeah.
So let's use this on our pitchers eligible career stats Hall of Fame Sands 2018 TBT. So the people that have been eligible for a few years now but have not gotten into the Hall of Fame for whatever reason. So we're going to take that data set, select everything from player to SO, and grab the inducted column and call that test. Again, as always, because R is so wonderful with their methods here, we've got this predict function calling the final random forest using our test data set to create the pred Hall of Fame in our test data set here. Just as we did before, we're also going to get our probabilities because it's kind of nice to see not just the flat value, but also the predicted value. So again, take test, toss that into predict. This time we're going to use type equals prob and rename the zeros to not inducted and 1 to inducted. Take ahead of that. That's kind of a little bit wide. It's not super easy to read. But let's look at the predictions for. Let's look at what are the total number that they predicted to get in, because obviously nobody actual is all false for everybody, and we've got 2 people that it predicts should get in, and 38 that don't. But who are those? So let's take the test data set, select the columns that we care about. We're not going to look at the statistics because I don't know. We're not looking at that. Who are the players that we think should get in or not? So select player ID, inducted or not, predicted Hall of Fame, whether the model thinks they should or not, and then there are various probabilities. Take ahead of that. So did I totally mess that up? I did not. Okay, cool. So basically, we're thinking that these folks should get in, and I am totally spacing on their names right now.
Jamie Moyer. I don't know this. I think the third one is Francisco Rodriguez, Billy Wagner, Jake Peavy. Yeah, so it's cool. Yeah, we got some guys.
Yeah, should be good. Hopefully they do get in. I mean, our model isn't incredibly bullish on them. If we're at a 50% threshold, it's a 55% and 51.6%. So
Yeah. Mhm.
yeah, they could get in. You never know. Based on stats alone. But also, what about the new folks? What about the folks that were newly eligible as of this year? So this again, let's pull out the Stats Hall of Fame 2018, call that test 2. Same sort of steps that we've just been following here. And we've predicted only one person to get in. And
No, we predicted 0.
oh yeah, 0.
Column
I
0 and 1. Yeah. So we
yes.
predicted 0 at the 50% threshold, but we can see Bartolo Colon is
Yes.
dangerously close at 45, they call it 45%. So we
Yes.
can see that again, and then there's a large drop from there. So it's like most of these guys probably the model doesn't think are true Hall of Famers, given
Hmm.
that it is hard to get in. But
Yeah.
yeah,
There you go. So Bartolo Colon, good luck.
yeah, and that's a little bit about tuning random forest models using Tidyverse. So Tidyverse is super powerful. We've done some tidy model stuff, but this is just using Tidyverse and map functions in order to tune your machine learning models. If you want to see more kind of stuff like that, like tuning model parameters in Tidyverse or using Purrr, like and subscribe and put the comments down below on the YouTube channel so we can get back to you.
Yeah. And then with that, I think we're going to call episode 175 of TidyX. Thank you all so much for 175 episodes. As always, my name is Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
And my name's Patrick Ward. You can find me on X at OSP Patrick. The screencast is on X at tidy_explained. But easiest way to get to us is YouTube channel, like, subscribe, comments down below. We will be sure to get back to you. And if you enjoy the show and would like to contribute, we do have a Patreon page. We're really grateful for anything that you may want to contribute.
Thank you all so much and keep on exploring your world.